There's this one single, kind of counterintuitive idea that completely turned the world of artificial intelligence on its head. It's this wild story about why it turns out that massive-scale messiness is actually way more powerful than perfection. And believe me, it changed everything.
All right, so let's get right into it. The whole thing really starts with a fascinating question. I mean, think about it. In physics, right, you've got these beautiful, simple, and just incredibly powerful formulas like E=mc² that seem to explain the universe. So why on earth don't we have something like that for human language? Or, for that matter, for any science that tries to model our own behavior?
Well, it turns out there's a name for this. It's called physics envy. It's this nagging feeling that fields like economics or linguistics have, where they're looking over at physics with its elegant, simple truths, and they're just missing out.
And the contrast is just stark. Physics gets these neat, tidy rules for things like elementary particles. But when you try to model human language, you're dealing with us. And we are not simple. I mean, the source material points out that a full grammar of English can run over 1,700 pages, all because it has to account for every single one of our weird, unpredictable quirks.
So, faced with all this complexity, how did computer scientists first try to solve this? They went with what seemed like the most obvious approach. If the system is that complex, well, you're going to need an equally complex, handcrafted set of perfect rules to figure it out.
And the absolute gold standard for this old way of thinking was a dataset called the Brown corpus. This thing was a massive undertaking. 1 million English words, all carefully chosen, all perfectly organized. And back then, this was what they called big data. It's kind of hard to even imagine now, but yeah, this was the top of the mountain.
This really sums up the whole philosophy of the time. The thinking was, if you want to build a smart system, you absolutely need a small, perfect dataset that's been meticulously labeled by experts. The goal wasn't just to make something that worked, it was to create these grand, elegant theories about how language itself functions.
But then the internet happened. And along with it came this absolute flood of something totally different. Massive, messy, completely unfiltered data.
And the scale of this shift is just mind-boggling. We went from that 1 million word Brown corpus to the Google Web corpus, which back in 2006 had 1 trillion words. That's 1 million times bigger. It's like going from reading a single book to having a library the size of a city. So yeah, the old data was clean, but it was tiny. This new web-scale data, it's a complete mess. Typos, broken sentences, you name it. But, and this is the key, its gigantic size means it captures everything, including all the rare, weird, and unusual ways we actually talk to each other. And that, as it turns out, is its secret weapon.
Okay, so why? Why is this so effective? Why does a huge pile of messy data just consistently demolish a small, pristine dataset? The answer is so simple, but it's incredibly powerful.
And here it is, the big idea, the core principle. Are you ready? A simple, even kind of dumb algorithm with a ton of data to learn from will almost always crush a super complex, elegant algorithm that only has a little bit of data. See, we didn't need a better theory, we just needed way more examples of reality. And this idea? It's literally the engine behind everything from your spam filter to what Netflix decides you should watch next.
A perfect example of this is a really simple model called an n-gram. It doesn't understand grammar or anything like that. It's basically just playing a massive game of what word is most likely to come next based on everything it's seen before. Now, with a little bit of data, it's pretty terrible. But you train it on 1 trillion words, suddenly that simple act of memorizing patterns becomes unbelievably good at stuff like machine translation.
Let's make this a little more real with a visual example. Okay, imagine you're trying to digitally remove an object, or, as the source paper cheekily puts it, an ex-spouse from a photo, and then you have to fill in the background so it looks natural.
So, the first attempts at this, using a few thousand photos, they were a total failure. Just awful. But then, researchers took the exact same simple algorithm and fed it a data set of millions of photos. And bam, the results were suddenly impressive. There was a data threshold. Once they crossed it, the simple model just worked.
So if this principle is so incredibly powerful, how does it apply to one of the biggest challenges on the web right now, teaching computers to understand not just our words, but the actual meaning behind them?
So this is where we need to be really clear about 2 concepts that people mix up all the time. On one hand, you have the semantic web.
That's the old school way, trying to create perfect, hand-coded rules so software can talk to other software flawlessly. On the other hand, you have semantic interpretation. That's the new way, using statistics on massive web data to figure out our messy, ambiguous human language. So one is about creating perfect rules for computers, and the other is about learning from our imperfect language.
And that old rule-based semantic web, it just runs into these huge practical problems. I mean, writing these rule books, they're called ontologies, is incredibly slow and expensive. The source article actually quotes a cost of $10,000 per page. It's a nightmare to implement, and it depends on everyone agreeing on the same rules, which, let's be honest, it's a huge social challenge.
So, okay, if hand-coding all these rules is basically a dead end, how does a data-driven way solve a simple problem like ambiguity? For example, how does a computer figure out that HP in a list with Apple and Microsoft means Hewlett-Packard and not something else?
Well, the data-driven solution is just beautiful in its simplicity. It doesn't need a rule book. It just looks at millions and millions of tables that people, actual humans, have already made on the web. It sees that we often put HP in the same column as Apple and IBM. It just notices these patterns of co-occurrence, and from that enormous mountain of evidence, it makes a very, very educated guess. No complicated rules, just observation on a massive scale.
All of this brings us to a final, really profound lesson that has pretty much become the defining principle of all modern AI.
The authors of the paper put it perfectly. They said, choose a representation that can use unsupervised learning on unlabeled data, which is so much more plentiful than labeled data. What they're saying is, stop trying to create perfection. Just use the vast, messy world exactly as it is.
So, the new rules of the game are actually refreshingly simple. Rule 1, follow the data. Rule 2, stop trying to squeeze the complex world into a simple model. Instead, let the immense detail in the data build the model for you. And Rule 3, trust the language we already use. The words and concepts that humanity has been building for thousands of years, that's an incredibly rich treasure trove of information.
So we're left with this incredibly powerful idea that simple methods, when you fuel them with massive amounts of data, are just unreasonably effective. This one principle has totally reshaped our digital world. And it leaves us with one last thing to think about. If the data really holds so many of the answers, what are the next questions that we should be asking it?